everyone. Good morning to respected Dr. Paresh Patel sir, beloved lecturers and dear students. Myself Khushbu Desai, on behalf of KBS in NATARAJ College, Vapi, welcome you all the participants for an exciting session on symmetry and group theory in chemistry and its applications. I extend my sincere warm welcome to the resource person Dr. Paris Patel sir for today's webinar. Sir, the previous live session of your lecture was very engaging and interesting. We are very grateful to you, sir, for all your efforts given to the students. Thank you, sir, for providing your valuable time with us. Now, I request Dr. Paris Patel, sir, to continue further with today's session. Over to you, sir.
Thank you, Khushbu madam. Good morning, dear students. Yesterday we discussed about the great orthogonal theorem, and with the help of the characteristics of the irreducibility presentation, we already derived the character table for C2V point group, C3V point group, and we also discussed about the different areas of the character tables. So, dear students, today we are going for the application portions, applications of the group theory in atomic orbitals as well as in sigma bonding. So, let us start with the first applications of group theory in the in the orbitals, atomic orbitals. We know that with the help of group theory and character table, we can predict the contribution of atomic orbital in the bonding skeletal of the molecules. So let us start with the help of the group theory. So applications of the group theory in the bonding, uh, we know that the relation between x is equal to r sine theta cos phi and y is equal to r sine theta sine phi and z is equal to r cos theta. Now this is the Cartesian coordinates, and we can convert into Cartesian coordinates into polar coordinates can be represented as px is equal to r sine theta cos phi, py is equal to r sine theta sine phi, and pz is equal to r cos theta. So by operating different symmetry operations on this molecule, theta remains unchanged, changes to only phi to that rotation. So dear students, how to find out the contribution of orbitals in the bonding skeletal of the molecules? So we know that the shape of the s orbital is spherical, shape of p orbitals is a dumbbell shape, and we also know about the shape of the d orbitals. So we have to operate different symmetry operation on the s orbital, p orbital, and d orbital and find out the changes. And that changes can be represented in form of the matrix, and we can derive the reducible representation, and from reducible representation, we can derive irreducible representation. Now compare that irreducible representation with the character table of that point group, and we can find out the contribution of that orbital in the bonding skeletal of the molecules. So let us start first with the water molecule. Applications of group theory in bonding of water molecule. We know that water molecule consists E, C2, sigma V XZ, and sigma V YZ symmetry elements. Now, first of all, what is the contribution of s orbital in the s orbital of the oxygen atom in the water molecule? We have to operate different symmetry operation. First, s orbital. Now, contribution of s orbital in the bonding skeletal of the water molecule. So we know that the shape of water molecule as shape of s orbital is spherical. Now, if we operate different symmetry operation on the spherical shape of the oxygen atom of the water molecule, then find out the changes. C2V, E, C2, sigma V XZ, and sigma V YZ. Now, if we operate different symmetry operation on the spherical shape of the oxygen atom of the water molecule. So first, if you operate identity symmetry operation on the spherical shape of the s orbital, so there is no change. It means character can be assigned as a +1. Now, if you operate different symmetry operation on the different orbitals and if it remains unchanged, so character can be assigned as a +1. If it changes to opposite, so we have to assign character -1. So in this case, if we operate identity symmetry operation on the spherical shape of the s orbital, so there is no change in the spherical shape of the s orbital. So character is +1. If we operate C2, if we operate C2 in the spherical shape of the s orbital, so there is no change in the spherical shape of this molecule. So character is +1. Sigma Vxz, if you operate sigma Vxz, it means this is the molecular plane and there is no change in the spherical shape of the s orbital. So character is +1. Sigma Yz, if we operate sigma Yz symmetry operation, so there is no change in the spherical shape of the s orbital. So character is 1. Now, whenever we talk about the C2V point group, it corresponds to A1 irreducible representation. Okay, and from character table, we can predict that this is the contribution from s orbitals. Okay, so whenever we talk about the area number 3 of this character table, so that corresponds to contribution of s orbital in the bonding skeletal of the oxygen atom of water molecule. So dear students, uh, in case of the water molecule, if you operate different symmetry operation on s orbital, so there is no change, and to get the different irreducible representation as a, and which corresponds to a1 irreducible representation, it means this is the contribution of s orbital in the bonding skeletal of the molecule. Now we are going for the another one is the p orbital. Now in p orbitals, this is the character table for C2V point group, or we can say water molecule belongs to C2V point group. Now p orbital, now if we operate identity symmetry operation on px. We know that shape of p orbital is tumble shaped. If we operate identity symmetry on px, and we know that px can be represented as r sine theta cos phi. So if we operate identity symmetry operation on any molecule, it remains as it is. It means this is nothing but the r sine theta cos phi is equal to px. So there is no change in the position of the px. If we operate C2 symmetry operation on px, then what will happen? Theta remains unchanged. Phi changes to phi plus pi. So C2 r sine theta cos phi is equal to r sine theta cos pi plus pi. Okay, in case of C2, we have to rotate the molecule around 180. It means pi. So is equal to r sine theta cos A plus B is equal to cos A cos B minus sin A sin B. So cos phi cos pi minus sin pi sin pi is equal to r sin theta cos pi. The value for cos pi is equal to minus 1 minus sin pi is equal to 0. So this can be represented as minus r sin theta cos phi is equal to minus px. So px becomes minus px. Next, if we operate sigma v xz symmetry operation on px, sigma v xz r sin theta cos phi. Now, in case of sigma v xz plane, this is molecular plane, so there is no change in the position of the px. So this can be represented as sin theta cos phi is equal to px. Next one, if we operate sigma v yz symmetry operation on px, so sigma v yz r sin theta cos phi. So we know that reflection always at 180 degree. It means r sin theta cos pi plus pi is equal to r sin theta cos pi minus sin phi sin pi is equal to r sin theta, value for cos pi is equal to minus 1. So cos phi minus 1 minus sin pi is equal to 0. So overall result is 0 is equal to minus r sin theta cos phi is equal to minus px. Okay, so overall result is minus px. So if you operate identity symmetry operation to give a px, C2 symmetry operation to give minus px, sigma v xz symmetry operation to give Px, and sigma V Y Z symmetry operation to give minus Px. This one is the x-axis. Now, if we operate identity symmetry operation, we can also consider that the shape of the p orbital is dumbbell shaped, and if we operate different symmetry operation on the dumbbell shape of the p orbital, either px, py, or pz, and find out the changes, that can also be considered. So if we operate identity symmetry operation on the spherical shape of the p orbital, this is px orbital, so there is no change in the spherical shape of the p orbital. Suppose this one is plus and minus, so plus and minus remains as it is. It means character can be assigned is plus 1. In case of C2 symmetry operation, so if we operate C2 symmetry operation, so to change the position of the lobes of the sign of the lobes, so character can be assigned as minus 1. In case of sigma Vxj symmetry operation, and we know that this is molecular plane, so there is no change in the position of px, so character can be assigned as a plus 1. Similarly, if we go for the sigma V Yz symmetry operation, so to change the positions of the lobes plus and minus, it means character is equal to minus 1. Okay, and we already derived E can be represented as a plus 1, so character can be assigned as a plus 1. Here character can be assigned as a minus 1, character can be assigned as a plus 1, character can be assigned as a minus 1. So either we have to go for the different symmetry operation on the spherical, dumbbell shape of the p orbital, maybe on px, py, or pz, or we can directly put the value theta is equal to 180 in case of the rotation as well as in reflection to get the character as a reducible representation. So now we can compile the overall result as C2V E C2 sigma Vxz sigma Vyz as a 1, minus 1, 1, and 1. Now from character table, we can assign that this minus 1, this corresponds to B1 irreducible representation. And already it is mentioned in the third area of the character table. So this is nothing but the contribution from Px. Similarly, we can conclude that this is the contribution from Py and this is the contribution from Pz. Okay, so this is the contribution from px orbital in the bonding skeletal of the oxygen atom of the water molecule. So dear students, we can directly predict from this character table, but this is the confirmations by using group theory. Similarly, we can predict that C2V E C2 sigma Vxz sigma Vyz. So this is the contribution from Px. If you go for the Py and Pz, A1, 1, 1, 1, 1. So this is the contribution from PZ. This is the contribution from PX. And Y, it means this is the contribution from PY. 1, minus 1, minus 1, 1. This is the contribution from PY. So dear students, this is the transformation properties for P orbital, maybe Px, Py, and Pz. So this is the contribution from Px, this is the contribution from Pz, and this is contribution from Py. So these properties can be recognized as a transformation properties of p orbitals. We already derived the transformation properties of s orbital, and we can directly predict from the character table, that is the contribution of d orbitals. So dx square minus y square. So in the last fourth area of the character table, that represents the contribution from s orbital. So dx square minus y square. This is the contribution from dx square minus y square. So it corresponds to A1 irreducible representation. Again, dz square, it is also in the A1 irreducible representations. Then dxy, this is the contribution from A2. dxz, B1, and dyz, this is B2. Okay, so these are known as a transformation properties of p orbitals and d orbitals. So whenever we talk about the transformation properties of oxygen atom in the water molecule, so we have to first derive the contribution from s orbital, then px, and from that we can predict the contribution from py, pz, as well as the d orbitals. So dear students, these are the transformation properties. Now we are going for the total contribution from p orbitals. If we operate identity symmetry operations on p orbital, then what will happen? We know that if we operate any symmetry operation on the molecule, so molecule remains as it is, so there is no change on the px, py, and pz. So this matrix can be represented as 1 0 0 0 1 0 and 0 0 1. So here character can be recognized as a 3. If you operate C2 symmetry operation on Px, Py, and Pz. If you operate C2 on Px and Py and Pz, we know that we have to consider any molecule along the z-axis. It means there is no change in the position of Pz. So we can write that minus Px, Py becomes minus Py, and Pz remains as it is. So C2 can be represented as minus 1 0 0 0 minus 1 0 0 0 1. So character is equal to minus 1. Similarly, if you go for the sigma Vxj, Px, Py, and Pz. Now, if we operate sigma Vxz symmetry operation on Px, Py, and Pz, we know that there is no change in the position of the Px and Pz because both these orbitals are in the xz plane, but Py will be minus Py. So that can be represented as Px minus Py and Pz. So sigma Vxz is equal to 1 0 0 0 minus 1 0 0 0 1. Sigma Vyz Px, Py, and Pz. If you operate sigma Vyz symmetry operation on the Px, Py, and Pz, we know that Px is perpendicular to yz plane and Py and Pz are in the same plane. So Px becomes minus Px, Py and Pz as it is. So sigma Vyz is equal to minus 1 0 0 0 1 0 0 0 1. So here character is equal to 1, character is equal to 1. So all the symmetry operations can be represented in form of the matrix, and that matrix can be summarized as reducible representations. So C2V E C2 sigma Vxz sigma Vyz. The character is 3. C2 is minus 1, 1, and 1. So this is reducible representation. We can reduce this reducible representation into irreducible representations with the help of relation between reducible and irreducible representations. So here N1 is equal to 1 by 4. Order of a group for water molecule is equal to 4. Now these are the reducible representation. It means 3, 1, and 1. 3. Minus 1, 1, 1. It means minus 1. 1, 1, 1. It means plus 1. 1, 1 plus 1. So is equal to 1. So value for N1 is equal to 1. N2 is equal to 1 by 4. 3, 1, 1. It means 3. Minus 1, 1, 1 is equal to minus 1. 1, 1, minus 1. It means minus 1. 1, 1, minus 1. It means minus 1. So is equal to 0. So the value for N2 is equal to 0. N3 is equal to 1 by 4. So 3, 1, 1, 3. Minus 1, 1 minus 1 is equal to plus 1. 1, 1 plus 1. 1, 1 minus 1 minus 1. So is equal to 1. And value for N4 is equal to 1 by 4. 3, 3, 1, 1. Minus 1, 1 minus 1 plus 1. 1, 1 minus 1 minus 1. 1, 1, 1 means plus 1. So is equal to 1. So the value for N1 is equal to 1, N2 is equal to 0, N3 is equal to 1, N4 is equal to 1. C2V E C2 sigma Vxz sigma Vyz. N1 is equal to 1, it means A1 1 times. So 1, 1, 1, 1. A2 is equal to N2 is equal to 0, means there is no involvement of A2. Then B1 is equal to, N3 is equal to 1, it means B1 1 minus 1, 1 minus 1. And N4 is equal to 1. So 1 minus 1 minus 1, 1. So this is the contribution from, or we can say, so Px can be represented as A1 plus B1 plus B2. This is one dimensional. This is again one dimensional, and this is again one dimensional. So the character of A1 one dimensional, one dimensional, one dimensional. So we can predict that this is actually three dimensional, and this is the contribution from p orbitals. And we can predict that p orbital belongs to three different irreducible representation, and this is the confirmations that p orbital belongs to three different irreducible representation. So dear students, this is the contribution of s orbital, p orbital, and d orbital of the oxygen atom in the water molecule. Now, next molecule is a ammonia molecule. The contribution of s orbital, p orbital, and d orbital in the bonding skeletal of the nitrogen atom of the ammonia molecule. We know that ammonia molecule consists E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc symmetry elements. Now, first, let us start with the s orbital. If you operate identity symmetry operation, C3 plus, C3 minus, and sigma V symmetry operation on the spherical shape of the s orbital. So what will happen over here? If you operate identity symmetry operation on the spherical shape of the s orbital, so there is no change. It means character can be assigned as a plus one. If you operate C3 plus or C3 minus, so there is no change in the spherical shape of the s orbital, so character is plus one. And if you operate sigma V symmetry operation, so there is no change, it means character is one. So this corresponds to even irreducible representations of C3b point group, or we can say this is the contribution of s orbital. Now p orbitals. Z, RZ, X and Y, RX, RY, X square plus Y square, Z square, X square minus Y square, XY, XZ, and YZ. Dear students, આ કેરેક્ટર ટેબલ છે તમને એક્ઝામમાં જે રીતે આપણે લોક ટેબલ પ્રોવાઈડ કરીએ છીએ તે રીતે તમને આ કેરેક્ટર ટેબલ પણ પ્રોવાઈડ કરવામાં આવશે. Now p orbital contribution from the p orbital. Suppose first one is px and py and pz. E into px, E into r sin theta cos phi. So there is no change in the dumbbell shape of the p orbital, e into py. So there is no change in the pz. Just a minute. It should be sine theta sine phi. And r cos theta is equal to pz. So by operating identity symmetry operation on px, py, and pz, so there is no change in the uh, shape of the p orbitals. Now, if you operate C3 symmetry operation, either C3 plus or C3 minus on Px is equal to C3 r sine theta cos phi is equal to theta remains unchanged and phi changes to pi plus 2 pi by 3. In case of ammonia molecule, we have to rotate this molecule along the main principal axis around 120 is equal to r sine theta cos pi cos 2 pi by 3 minus sine pi sine 2 pi by 3 is equal to r sine theta. Now the value for cos 2 pi by 3, cos 2 pi by 3 can be represented as a minus 1 half cos phi, and value for sine 2 pi by 3 is root 3 by 2 sine phi. So is equal to minus 1 half r sine theta cos phi minus root 3 by 2 r sine theta sine phi. Or we can say this is nothing but the 1 by 2 px and minus root 3 by 2 py. So if we operate C3 symmetry operation on px, py, and on px to give minus 1 half px minus root 3 by 2 py. If you go for the py, then C3 plus r sine theta sine phi is equal to C3 plus, it means r sine theta sine pi plus 2 pi by 3 is equal to r sine theta sine a plus b is equal to sine a cos b minus plus sine a cos b. So sine pi cos 2 pi by 3 plus cos pi sine 2 pi by 3 is equal to r sine theta sine pi cos 2 pi by 3 is equal to minus 1 half, and sine 2 pi by 3 is equal to root 3 by 2 cos pi is equal to minus 1 half r sine theta sine pi plus root 3 by 2 r sine theta cos pi is equal to minus 1 half py plus root 3 by 2 px, or we can say root 3 by 2 px minus 1 half py. So py can be represented as root 3 by 2 px minus 1 by 2 py. Similarly, if we operate C3 plus on Pz is equal to R cos theta, there is no change in the Pz, or we can say this is nothing but the Pz. Now, if we operate sigma V axial symmetry operation on Px is equal to in case of the Px xz, this is in the same plane. It means there is no change in the sigma V xz r sine theta cos phi is equal to x. Now, if we operate sigma V yz symmetry operation on Py, then it is also in the same plane. Sorry, xj on the Py. So this is perpendicular. Okay, if you operate any symmetry operation on Px, Py, and Pz, answer will be the same. So in case of C3V, if you operate sigma V on Px. Now in case of Px, ammonia molecule consists all the three planes of yz plane. So sigma V r sine theta cos pi cos phi. So here Px is perpendicular to the yz. It means r sine theta cos pi plus pi, because reflection always at 180. So is equal to r sine theta cos phi cos pi minus sin pi sin pi is equal to r sine theta, value for cos pi is equal to -1. So minus cos phi, and it becomes 0 is equal to minus px. Now in case of the Py, so it is in the same plane, yz plane. So there is no change in the r sine theta sin phi is equal to Py. Similarly, in case of Pz, this is also in the same plane, sigma V r cos theta is equal to Pz. So these are the contribution from Px, Py, and Pz. Now we can predict that these are the contribution from Px, Py, and Pz in the bonding skeletal of nitrogen of ammonia molecule, or we can predict that These are the transformation properties of px, py, and pz of the nitrogen atom of the ammonia molecules. Now, if we operate combined symmetry operation on p orbital, then what will happen? E into px, py, and pz. So there is no change in the position of px, py, and pz. So this matrix can be represented as 1 0 0 0 1 0 0 0 1. So character is equal to 1 plus 1. C3 plus or C3 minus on px, py, and pz. So if we operate px, py, and pz, then what will happen? We already derived the matrix representations for px, py, and pz. So px is equal to minus 1 half px and minus root 3 by 2 py. So that can be represented as minus 1 half and root 3 by 2, 0. Again, minus root 3 by 2, root 3 by 2, minus 1 half, 0, 0, 0, 1. This is a derivation from px, py, and pz. So C3 plus or C3 can be represented as minus 1 half root 3 by 2 px, py, and pz is equal to, so C3 plus can be represented as minus 1 half minus root 3 by 2, 0, root 3 by 2 minus 1 half, 0, 0, 0, 1. So here character is equal to 0. Minus 1 minus 1 half is equal to 0. And sigma VA px, py, and pz. So if we operate px, py, and pz, sigma v on px, py, and pz. So all the three planes are the y-z plane. So px becomes minus px, py remains as it is, pz remains as it is. So sigma v can be represented as minus 1 0 0 0 1 0 0 0 1. So character is equal to 1. Okay, this is the matrix representation for identity symmetry operation. This is the matrix representation for C3, and this is the contribution from sigma v. Now we can summarize that. C3v E twice C3 3 sigma v. So we can reduce this three-dimensional matrix into two-dimensional and one-dimensional. X and Y. So 1 0 0 1. and 1. This is the contribution from Z orbitals. Similarly, we can reduce the C3 plus into two-dimensional and one-dimensional and sigma V. So that matrix can be represented as minus 1 half minus root 3 by 2 root 3 by 2 minus 1 half and 1 minus 1 0 0 1 and 1. Okay, so dear students, we can predict that p orbital belongs to two-dimensional and one-dimensional irreducible representations in case of nitrogen atom of the ammonia molecule. So here character is equal to 2, character is equal to 1. So we can reduce the three-dimensional representations into two-dimensional and one-dimensional. So dear students, this is the applications of group theory in the atomic orbitals. So with the help of group theory, we can predict the contribution of s orbital, p orbital, and d orbital. Now we are going for the another applications of the group theory, that is applications of group theory in the bonding. Only sigma bonding is in our syllabus, so we can predict the how many hybrid orbitals involved in the bonding skeletal of the molecule. So let us start the applications of group theory in the sigma bonding. Now, how to get the applications of group theory in the sigma bonding? So, first of all, find out the symmetry elements are present in the molecule and and consider the bonding in form of the vectors and operate different symmetry operation on that vectors and find out the changes. Okay, and changes can be represented as if unchanged character is +1, changes to opposite character is -1 to derive the reducible representation, and from reducible representation we can reduce that reducible representation into irreducible component and compare that with the character table of that matrix and character table of that point group and find out the how many hybrid orbitals are involved in the hybridization. So let us start with the first molecule of the sigma bonding. Applications of group theory in the sigma bonding is the BCl3 molecule. Now we know that shape of ammonium a BCl3 molecule is planar molecule, and we can consider this BCl3 molecule as a three hybrid wave function, psi h1, psi h2, and psi h3. Now consider that hybrid wave function as a in form of vectors as a v1, v2, and v3. Now operate different symmetry operation of BCl3 molecule on the vectors and find out the changes. We know that BCl3 molecule consists E twice C3, or we can say C3 plus C3 minus, and 3C2 sigma H twice S3 and 3 sigma V symmetry elements. Now if we operate identity symmetry operation on V1, V2 and V3, so there is no change in the position of vectors V1, V2, V3. So matrix can be represented as 1 0 0 0 1 0 0 0 1. Now if we operate C3 plus, then what will happen? This one is the C3. If you operate C3, it means C3 plus, then 0 into V1, 1 into, yes, 1 into V2, 0 into V3, 0 into V1, 0 into V2, and 1 V3, 1 V1, 0 V2, 0 V3. So in this one, 0 1 0 0 0 1 1 0 0 V1 V2 V3. So here the character for C3 plus is equal to 0 1 0 0 0 1 1 0 0. It means character is equal to 0. So by operating C3 plus, there is no change in the character is equal to 0. D3H, E to YC3, 3C2, sigma H twice S3 and 3 sigma B. So the character for identity is 3. Here 0. Now if we operate C2 symmetry operation on the vector V1 and V2, V3, then what will happen? V1, V2, V3. This is C3. And if we operate C2 symmetry operation, so there is no change in the position of the only one vector and remaining two vectors are interchanged. So if we operate C2 symmetry operation on V1, V2 and V3, then what will happen? So 1 into V1, 0 V2, 0 V3, 0 V1, 0 V2, 1 V3, 0 V1, 1 V2, 0 V3. It means the position of the one vector remains as it is. So that can be represented as 1 0 0, 0 0 1, 0 1 0. So character of this matrix is equal to 1. So that can be represented as 1. Now sigma H. If we operate sigma H on the symmetry operation, sigma symmetry operation on the three vectors, it means there is no change in the position of the all the vectors. So character is 3. S3. S3 means first of all we have to go for this C3 plus and followed by the sigma H. So character can be assigned as a 0. In case of the sigma V, it means there is no change in the position of the only one vector and two vectors are interchanged. So character is plus 1. So dear students, these are the reducible representations. This is the reducible representations for the sigma bonding in BCl3 molecule. Now we can reduce this reducible representations into irreducible representations, and with the help of the character tables as well as relation between reducible and irreducible. So here value for n1 is equal to 1. Then it n2 is equal to also 0, n3 is equal to 1, n4 is equal to 0, n5 is equal to 0, n6 is equal to 0. It means T sigma is equal to n1 is equal to 1. We can represent as a1 dash and e dash. If we compare the character table, આપણે character table જોઈશું તો third અને fourth એરિયામાં આપણને મળશે this is the contribution from s orbital, and third એરિયામાં આપણને મળશે px and py, and fourth area dx square minus y square and dxy. Dear students, આપણે એનું કેરેક્ટર ટેબલ જોઈશું BCl3 નું તો આપણને થર્ડ એરિયામાં x અને y લખ્યું છે. It means this is the contribution from px and py, and in the last column that can be considered as a x square minus y square and the xy. It means that is the contribution from dx square minus dxy as well as dxy. So we can predict that the hybrid orbital in the BCl3 molecule can be involved either sp2 hybridization or sd2 hybridization. But we know that p orbital is closer in energy. So hybrid orbitals in BCl3 molecule can be formed by sp2 hybridizations. So dear students, this is the sigma bonding in BCl3 molecule. Now we are going for the last molecule of the sigma bonding, that is ammonia molecule. Size 1, size 2, size 3. Let us consider hybrid orbitals in form of the vectors. Now find out the symmetry elements are present in ammonia molecules. E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. So how to find out the contribution of hybrid orbitals? So first of all, find out the symmetry elements are present in a molecule. Then consider all the hybrid orbitals in form of the vectors, and operate different symmetry operation on the vectors and find out the changes to get the reducible representation, and reduce that reducible representation into irreducible component, and then compare that irreducible component with the help of the character table, so to give the contribution of hybrid orbitals in the sigma bonding of the molecules. So in case of the ammonia molecule consists E, C3 plus, C3 minus, sigma Va, sigma Vb, sigma Vc symmetry elements. Now consider three hybrid wave function in form of the vectors as a V1, V2, and V3. Now operate different symmetry operation on V1, V2, and V3. This is C3V, E to YC3, and 3 sigma V. Now if we operate identity symmetry operation on V1, V2, and V3, so there is no change in the position of the vectors. So 1v1, 0v2, 0v3, 0v1, 1v2, 0v3, 0v1, 0v2, and 1v3. So is equal to 100, 010, 001, V1, V2, and V3. So character is equal to 3. So this can be represented as 3. If we operate C2, C3, C3 symmetry operation, then what will happen? 0 into 1, 1. Change the position of all these vectors. So here character is equal to 0. And if we operate sigma v, so in case of the sigma v, what will happen? There is no change in the position of the one vector and two are interchanged. One into v1, 0 into v2, 0 into v3, 0 into v1, 0 into v2, 1 into v3, 0 v1, 1 v2, 0 v3. So is equal to 1 0 0, 0 0 1, 0 1 0, v1, v2 and v3. So this sigma v can be represented as a character is equal to 1. C3v E twice C3, 3 sigma v, A1, A2, E, 1 1 1 1 1 minus 1 1 2 minus 1 0, and Z RZ XY RX RY x square plus y square z square x square minus y square xy xz and yz. This is the character table for C3b point group. Now in case of the this is reducible representations, and from this reducible representations we can reduce the reducible representation into irreducible representation by using character reducible representations into character I into R. So by using these equations and with the help of this character table, the value for n1 is equal to 1, n2 is equal to 0, n3 is equal to 1. So we can predict that T sigma is equal to A1. N1 is equal to 1 means A1 plus E. Now we can predict that from A1, this is the contribution from PZ as well as S orbital. S orbital as well as PZ orbital. E, this is Px and Py. X and Y, it means Px and Py. And this is the contribution from dx square minus y square, dxy. Dx square minus y square, dxy, and dxz and dyz. So we can predict that in ammonia molecule, The hybrid orbitals can be formed by either sp2 hybridization or sd2 hybridization. But we know that p orbital is closer in energy. So hybrid orbitals in the ammonia molecule can be formed by sp2 hybridization. So dear students, this is the applications of group theory in the sigma bonding. So dear students, I think this is the enough for today's discussion, and this is the end of our session of the molecular symmetry, group theory, and its applications. So thank you very much for listening me very silently. And once again, I am very, very thankful to the principals of the KBS College, as well as coordinator Khushbu Desai Madam, for providing me with these facilities or providing me this platform to share my views. Thank you very much.
Thank you, Dr. Paresh Patel, sir, for facilitating such a positive learning environment. We really enjoyed and learned a lot, sir. All the sessions were full of knowledge with interesting examples, and it gave us deep insights into the topic. Dear all, I feel grateful to have the presence of our Honorable Principal, Dr. Poonam Chauhan. I heartily welcome you, ma'am. I request Dr. Poonam, ma'am, to speak a few words about the session. Over to you, ma'am.
Thank you, Khushbu. I'm really, sir, very much thankful to you for giving your time and your inspiring presentation. I heartily appreciate the information, the knowledge that you have shared and enriched the minds of students and other participants who are being the part of this session. And I hope that we will continue the same in the coming time. And once again, sir, I'm very much thankful for being the part of our institution and sharing your valuable experience and knowledge with all the participants. Thank you so much, sir.
Thank you, madam. Thank you, madam,
Yes, sir,
for
thank you.
providing me this platform uh, to share my views to all the students of Veer Narmad South Gujarat University students. So whenever I need the platform, so you always ready. So thank you for that, madam. So
And we are,
once
sir.
again, thank you, madam, and thank
Thank
you,
you.
Khushbu, madam. Thank you, dear students, for uh, okay. Thank you,
Once
madam.
again, once again, sir, I would like to thank you for being with us and providing your valuable time from your busy schedule and enlightening us with the knowledge. Thank you so much, sir. We are very grateful to you, sir. And I also would like to thank our principal, Dr. Poonam Chauhan, for all your kind support to organize the live webinars. Without your support, this was not possible, ma'am. Thank you very much, ma'am. And on the behalf of KBS and NATARAJ College, I would like to express sincere appreciation and gratitude to all the participants for all your immense responses. We will back soon with another webinar series. Thank you all. Goodbye, everyone, and have a nice day. Goodbye, all.
Thank
Goodbye,
you, madam.
sir. Goodbye, ma'am.